Hey guys, welcome to your first lesson of Chapter 13 on using trigonometry with right triangles. A lot of this should be reviewed to you guys as we kind of look at some of the things that we talked about way back in geometry, but we're going to kind of take it to a new level in Algebra 2. So first of all, just a couple of definitions. Sine, cosine, tangent, secant, and cotangent are basically the 6 basic trigonometric functions that consist of the ratios of a right triangle's side lengths. All right, and so how we define those ratios are as follows. All right, the sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent becomes the opposite over the adjacent. All right, and that should really be nothing new to you. You guys should be familiar with those ones already. One of the things that we talked about in geometry was this saying SOHCAHTOA, which told us that the sine ratio was the ratio of opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So those ratios we've kind of already defined. Now the new ones that we have to define are what are referred to as cosecant, secant, and cotangent. All right. The cosecant is essentially the reciprocal of the sine ratio. All right. So the sine of some angle theta is opposite over hypotenuse, and so the cosecant would then be the reciprocal, or hypotenuse over opposite. The cosine is adjacent over hypotenuse, and so the secant is then the hypotenuse over adjacent. And then the cotangent would then be the reciprocal of the tangent ratio. Again, cotangent goes with tangent. That one seems to make a lot of sense. All right. One of the things that I like to remember is that a C goes with an S. Okay, so sine and cosecant. And then cosine and secant have to go together. So that might help you a little bit. And then obviously tangent and cotangent, should be able to figure those ones out. So down below they just talk a little bit about the idea that, look, the cotangent is the reciprocal of tangent, the secant is the reciprocal of cosine, and the cosecant is the reciprocal of sine. All right? So I want to take a look at the next page then. Sorry about the scrolling text there. Let's evaluate the 6 trigonometric functions of this following triangle. And so we're going to use this angle theta as our reference angle. And so the first thing we need to do is we need to find the hypotenuse of that right triangle. Well, to do that, we have to use our old Pythagorean theorem. So this becomes 8 squared plus 15 squared is equal to, and we'll call it c squared for now. All right? And so this becomes 64 plus 225. And 64 and 225 comes out to 289. And so c squared is equal to 289. Take the square root. C equals really plus or minus the square root of 189, which is 17. But we don't have to consider plus or minus because the length has to be positive. And so we know that this is equal to 17. And so now we know the hypotenuse is 17. Remember, the sine ratio is opposite over hypotenuse. Okay, so the side opposite that angle theta is 8 over the hypotenuse, which is 17. Because of that, then, the cosecant is the reciprocal of that, or hypotenuse over opposite. Well, hypotenuse over opposite now becomes 17 over 8. The cosine of that angle theta is adjacent over hypotenuse. And again, remember, you've got that saying SOHCAHTOA that helps us to remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. All right, so that's something you probably want to write. And that will help you define at least the initial 3 that we're familiar with, and then remember which one's the reciprocal of which. I guess is the best way to talk about that then. All right, so the adjacent side to angle theta is the 15. I realize that 17 is adjacent to that angle as well, but the one that's opposite the right angle is the hypotenuse. That's the 17. So when we talk about the adjacent side, that's 15 over 17, and so therefore the secant is going to be the reciprocal, or hypotenuse over adjacent, which in this case would be 17 over 15. All right, finally, the tangent ratio then becomes opposite over adjacent, and so the opposite side would be the 8, and then the adjacent's the 15. And so as you can tell, the cotangent then is going to be 15 over 8. All right? Now, this next box, all of the rest of this stuff, really, this comes from very special triangles, and having a special right triangle in which we have a 45-45-90 triangle, which basically becomes an isosceles right triangle. We talked more about this in geometry and really spending a lot of time with these special right triangles. But the ratios of these sides are as follows. So first of all, let's start with the 30-degree triangle, the 30 and the 60-degree triangle. All right? So looking at this triangle down here, all right, we can fill in some of these angles here. So for a 30-degree angle, again, the ratios of these sides can be anything you want. This could be 2x, this could be 1x, this could be radical 3 times x. Whatever these quantities are, they'll always be in this ratio. all right? And it has to do with this fact that these angles in this particular triangle are 30, 60, and 90, okay? So the ratios of the sides are always going to follow this ratio. And so therefore, the sine of angle of a 30-degree angle will always be the opposite over the hypotenuse. Well, in this case, the opposite is 1, the hypotenuse is 2, and so that will be equal to 1/2. The cosine will be the adjacent side, which in this case is radical 3 over the hypotenuse, which is 2, so that's simply radical 3 over 2. Now the tangent becomes the opposite, which is 1, over the adjacent, which is radical 3. So we get 1 over radical 3. Now, back in chapter 4, we talked about the idea of how to simplify this radical. We really didn't do a lot with this in chapter 3, but basically if we multiply top and bottom of this by the square root of 3, we're basically just multiplying by 1, all right? And so this becomes 1 times radical 3, which is simply radical 3, and then radical 3 times radical 3 is the same thing as radical 3 squared. Well, we know that squaring and square root undo each other, and so a better way to write the tangent of a 30-degree angle is the square root of 3 over 3. All right, let's jump down to that 60-degree triangle. Let's do a different color here, so let's change to red here. So for the 60-degree angle now the opposite side, when I go to define the sine, that would be the opposite, which is radical 3 over the hypotenuse would be radical 3 over 2. And you'll notice that the sine of angle theta is the same as the cosine of angle theta. And part of that has to do with the fact that basically your opposite and adjacent sides are switched. All right? You'll notice that these are opposites as well. All right? Because now when I go to find the cosine of a 60-degree angle, the cosine is the adjacent over the hypotenuse. Well, that's 1 over 2, which is 1/2. And then finally, when I go to find the tangent of a 60-degree angle, that's opposite over adjacent. Well, that's radical 3 over 1, which is simply radical 3. All right, so now we've defined all of those things. Now we could go through and we could do the cosecant and the secant, the cotangent of 30 and 60 degrees as well. So again, the cosecant is the reciprocal of this. So if I flip over, 1 over 2 becomes 2 over 1. This one's a little trickier. We'll deal with that in just a minute. But if I wanted to find the secant, then the secant is the reciprocal of cosine. All right, so if I flip over this cosine up here, this becomes 2 over radical 3. And what we talked about before is multiply top and bottom by radical 3. And so this becomes 2 radical 3 over 3. And that's where they're getting that right here. All right, now the cotangent, I can certainly flip this around if I wanted to. But I'm going to go back to what I started with over here. When I found the tangent of a 30-degree angle, that was 1 over radical 3, and so the cotangent then would be the reciprocal of that, which is radical 3 over 1. Now for a 60-degree angle, you'll notice that these two are switched, and these two are switched, which effectively is kind of what we should have been expecting. And then so now if we kind of take a look at this, well, the cosecant of a 30-degree angle will be the reciprocal then, and so the secant of a 60-degree angle will be 2, and vice versa. All right, now, I'm going to give you a much better way to do all of this. Over the next couple of days, we're going to be talking about a video series where we talk about something called the unit circle, and that'll make a lot of this make a lot more sense. But for right now, you need to know these values, and you can refer to this in your textbook when you do your assignment for today. Eventually, you won't need this table anymore, which I think is really, really, really important. Okay? All right, so I'm going to switch now to a nice dark black color. Let's do the 45, 45, 90 triangle. Remember, in a 45, 45, 90 triangle, the ratio of the sine will be opposite over hypotenuse. Well, that's 1 over the square root of 2. Well, 1 over the square root of 2, if I multiply top and bottom by radical 2, this becomes radical 2 over 2. And so that's where they're getting that number right there. Now, the cosine is going to be the adjacent over hypotenuse. Well, the adjacent is also 1. And so we're going to get the exact same thing. And so this should also be radical 2 over 2. Okay, now what if I was going the other way? What if I was finding the cosecant of a 45-degree angle? Well, the cosecant of a 45-degree angle is going to be hypotenuse, radical 2, over the opposite side. So if I'm using this 45-degree angle, it's going to be square root of 2 over 1, which is simply the square root of 2. And the same would go then, and again, it's because the opposite and the adjacent sides have the exact same length is why these two will match and these two will match. All right. Now remember, tangent is opposite over adjacent. Well, if the opposite and the adjacent are both the same number, 1 over 1 is simply 1. Okay, so like I said, we're going to get into a method to remember that a lot better called unit circles, but for right now I just wanted to at least throw those values at you. Let's take a look at how we would do it if it's not one of our special triangles. Okay, so we would use a calculator to solve a right triangle. The first thing we have to understand and remember is that there's 180 degrees in any triangle. All right, so 180 degrees for the whole thing. I've got 90 of those degrees knocked out right there at angle C, so that says I have 90 degrees left over to share between angle A and angle B. So angle A and B have to be complementary angles. 90 minus 56 tells me that this is 34 degrees. All right, and so this is 34 degrees. Now we found all of the angle measures. Now we need to find one of those lengths. We already have, in relation to this 56 degree angle, I already have the adjacent side. I would like to find the opposite side. So I'm going to say the tangent of angle B is equal to the adjacent side over the, opposite side over the adjacent side. All right? And so this becomes opposite over adjacent. All right? So then the opposite side is B, the adjacent side is 13. Now I'm going to make this into a ratio so I can do cross products. 13 times the tangent of 56 and 1 times B is simply B. So one of the things you have to make sure of is make sure your calculator is in degree mode. Okay, your calculators come from the factory in what's called radian measure, which we'll discuss in much more detail in the next couple of videos. But radian measure is another way to measure an angle. Your calculator has to be in degrees. So if you simply type the tangent of 56 times 13, and I want to put the tangent of 56 after the 13. I'm going to do 13 times the tangent of 56. Otherwise, you might run into the problem of running the tangent of 56 times 13, and it's going to take whatever 56 times 13 degrees is and take the tangent of that. That's not what I want to do. Okay? So what I'm going to do with that instead is I'm going to put the 13 in the front. And then 13 times the tangent of that becomes 19.27. And so this side over here happens to be 19.27. All right? Once I have that, then I can say, well, I could use a lot of different ratios here. They're going to use the secant. And quite frankly, I wouldn't use the secant here. All right? If I'm trying to find the hypotenuse here, I know the adjacent side. I want the hypotenuse. So the cosine helps me find adjacent and hypotenuse, or at least relate them in one ratio. The cosine of 56 degrees is equal to the ratio of adjacent, which is 13, over the hypotenuse, which is C. So I'm going to put this over 1. I'm going to cross multiply. I get 13 equals C times the cosine of 56. Now the cosine of 56 is just a number. So I'm going to divide both sides by cosine 56. And I get C is equal to whatever 13 divided by the cosine of 56 is. According to my calculator, I get 23.25. All right, now, it makes sense that the hypotenuse should be the longest of those sides. If I wanted to check that by using Pythagorean theorem, I could do 13 squared plus 19.27 squared, and then make sure it's equal to 23.25 squared. Okay? All right, so checkpoint problem at the bottom of the page. I'm going to go to the 6 trig functions. You need sine of theta, you need the cosine of theta, you need the tangent of theta, and then we want all the reciprocals of those, which would be the cosecant of theta, the secant of theta, and the cotangent of theta. And again, these ones are written in this order because these two are reciprocals, these two are reciprocals, and those two are reciprocals. So the sine would be opposite over hypotenuse, so this would be opposite, which would be 12, over the hypotenuse, which is 4 radical 13. I'm going to leave my answer like that for now. What I could do then is I could say, look, 4 goes into 12 3 times. And so this is 3 over radical 13. 3 over radical 13. So then the cosecant would be the reciprocal of that, which would be radical 13 over 3. Sorry, there's supposed to be a 13 there. It's kind of hard to read. Let's clean that up a little bit. Yeah, that's better. All right, how about the cosine? Well, the cosine is going to be adjacent. That's my problem, is I don't know the cosine. So I'm going to call this x for right now. X squared plus 12 squared equals 4 radical 13 squared. Right? Using Pythagorean theorem, this becomes x squared plus 144 is equal to 4 squared is 16. The square root of 13 squared is 13. All right? and then I just have to do 16 times 13. And 16 times 13 comes out to be 208. And so this is x squared plus 144 equals 208 minus 144 from both sides. I get x squared is equal to 64. When I take the square root, I get x is equal to 8. All right, so now when I go to find the cosine, that becomes 8 over 4 radical 13. And since 4 goes into 8 twice, this is 2 over radical 13. And so the secant is going to become radical 13 over 2. Finally, to find the tangent would be opposite over adjacent, which becomes 12 over 8. And since those both have factors of 4, this becomes 3 over 2. And so therefore the cotangent would be 2 over 3. All right? In solving this right triangle, first of all, I would say 90 minus 37, and that tells me that this angle over here is a 53-degree angle. Okay, so I know angle B to be 53 degrees. Now I just have to find those missing sides. So the first thing that I want to do is I want to say, all right, in relation to angle A, I want the opposite side, and I have the hypotenuse. So the sine of a 37-degree angle is going to be equal to the opposite side, which is A over 22. From there, I'm going to make this into cross products, and A is equal to whatever 22 times the sine of 37 is. I know that's kind of hard to read, but if I do 22 times the sine of 37, I end up getting that side A is equal to 13.24. And that makes sense because it's shorter than the hypotenuse. Okay? To find side B, I want the cosine of 37 degrees, and that's equal to the adjacent side over the hypotenuse. And so I cross multiply, and I get B is equal to whatever 22 times the cosine of 37 is. Once again, make sure your calculator is in degree mode. I end up getting that side B is 17.57. All right? Finally, on the last page of this lesson then, talks a little bit about this idea of angles of elevation. Angles of elevation are a little bit confusing. Angles of elevation or angles of descent are always measured with the horizon of the perspective that we're looking from. So again, you're measuring the height of your school building. You stand 25 feet from the base of the school. All right? The angle of elevation from a point on the ground looking up, so we always start with a horizontal and we look up at an angle of elevation of 62 degrees. Estimate the height. Well, in this case, I want the opposite. I have the adjacent. Which relationship relates the opposite and the adjacent? Well, the one that has O and A, so that would be the tangent. So therefore, I would say the tangent of 62 degrees is equal to the opposite over the adjacent. From there, I'd make this over 1, and I'd cross multiply. And so H is equal to whatever 25 times the tangent of 62 is, and it comes out to be approximately 47 feet. All right, and so this is roughly 47 feet tall. All right, we'll save the checkpoint for your for in class tomorrow. You should get something in the neighborhood of 34 feet for the checkpoint problem. Why don't you try it? But you should be getting something like 34 feet. And if you have questions about that, definitely let's talk about that tomorrow. But that concludes your first lesson on 13.1.